This lesson focuses on the standard normal distribution. In this chapter, we will focus on the continuous random variables and normal distributions. A normal distribution is where the curve is bell-shaped and symmetric. This section presents the standard normal distribution. In the standard normal distribution, there are three properties for the curve. Its graph is bell-shaped, its mean is equal to 0, and its standard deviation, sigma, is equal to 1. Our goal in this chapter is to develop the skill to find areas, or probabilities, or relative frequencies that correspond to various regions under the graph of the standard normal distribution. We will also learn how to find particular z-scores that correspond to area under the graph. Another kind of distribution is a uniform distribution. A continuous random variable has a uniform distribution if its values are spread evenly over the range of probabilities. The graph of a uniform distribution results in a rectangular shape. A density curve is the graph of a continuous probability distribution. It must satisfy the following properties. The total area under the curve must equal 1 or 100%. And every point on the curve must have a vertical height that is 0 or greater. So the curve cannot fall below the x-axis. Because the total area under the density curve is equal to 1, there is a correspondence between area and probability. In a uniform distribution, each value of the random variable has the same probability. This creates a density curve graph in a rectangular shape. Here's a graph of a density curve that has a uniform distribution. So the total area under the curve must equal 1. So this is showing a class length limit for a particular course. Class times run between 50 and 52 minutes. So if we look at the distance on the x-axis from 50 to 52, that's a distance of 2 units. And since the total area under the curve must equal 1, then we choose the height to be 0.5 or 1/2. So that length times width for area of a rectangle will work out correctly. So 2 times 1/2 is equal to 1. So that's how we got this height here for the rectangular distribution. You can also work it out using the formula to backtrack. Area is equal to length times width, and we know the area under the curve must be 1. So we set 1 equal to the length times the unknown width. The length is 2. The width is y. If we solve for y, we're going to divide by 2. So the y height must be 1/2 or 0.5. Let's solve some problems using this uniform distribution. Kim has an interview right after class. If the class runs longer than 51.5 minutes, she will be late. Given the previous uniform distribution, find the probability that a randomly selected class will last longer than 51.5 minutes. Okay, so what I want to do is shade the region representing times that are longer than 51.5 minutes. So I go all the way up to the curve and shade that rectangle. And I know that area under the curve is length times width since this is a rectangular distribution. So the distance from 51.5 to 52 is 0.5. And then this height is also 0.5. So 0.5 times 0.5 is 0.25. So there's a 25% chance the class will last longer than 51.5 minutes. Find the probability that a time greater than 50.5 minutes is selected. Okay, so shade the region representing times that are longer then 50.5 minutes, and then find that distance and set up your area formula. So from 52 to 50.5, we want to subtract that to find the distance, and we know the height is 0.5. So that gives us an answer of 0.75 or 75%. Find the probability that a time between 51.5 minutes and 51.6 minutes is selected. So I need to estimate where this would be on the curve. So from 51.5 to approximately 51.6, I get this skinny rectangle. So I need to find that distance. So I subtract 51.6 minus 51.5, and I multiply that by 0.5. That gives me an answer of 0.05 or 5% chance. The standard normal distribution is a normal probability distribution with the mean mu equals 0 and sigma standard deviation of 1. The total area under its curve is equal to 1. So the mean 0 goes in the middle of the number line, and this is just a normal number line here. We have positive 1, 2, and 3 on the right and our negative numbers on the left. However, this is called a z-score axis. It's not an x-axis. The area under the curve is 1, so under this entire bell shape, 100% of my data will be graphed. If I draw a line exactly in the middle, then I know that I'm going to have 50% of my data to the right and the other 50% to the left. So when we are given z-scores, we have a bell-shaped curve. The mean is 0, standard deviation is 1. The total area under the curve is 1. Now all the values on the x-axis are z-scores. And to convert and figure out a z-score, the formula is x minus mu divided by sigma. Now the z-score refers to position. It tells you how many standard deviations above or below the mean a particular value is. In this formula, x is your data value. So that particular data value, if you want to convert it to a z-score, you subtract the mean from it and divide by standard deviation. The area under the curve is equal to the probability. However, since this is not a rectangle, it's a bell-shaped curve, and we're trying to find particular areas, we can't do length times width. So we have a table that calculates these areas for us. It's called Table A2. It can be found in a pull-out table in your textbook, or it's either located in the front cover or the back cover of your book. This table gives the area underneath the curve to the position of the left of the z-score. There are some methods for finding normal distribution areas. For instance, your calculator. If you have a graphing calculator, it will give you the area bounded on the left and the area bounded on the right when we look at specific values. So this slide just shows you how to type that in. For this course, we'll be using Table A2. Table A2 is the standard normal z distribution table. It always gives you cumulative area from the left of your mark on the curve. And so notice here we have our z's. That's going to be how we look these up. So if our z is on the curve, so the mean is 0, and let's say it's all the way at -4, and I want to know the area to the left of -4. Well, the area to the left is going to be 0.0001. Okay, so -3.5 and lower, that's going to be my area. Now you have specific values here, so the way that we read this is, let's say that my z is -2.73. So to look that up, I go to -2.7, and then I go up here, and this is my hundredths position of the decimal place. So I put that together and I align it, and this is going to be my area to the left of -2.73. Table A2 is designed only for the standard normal distribution. In the standard normal distribution, the mean is 0, standard deviation is 1. So only for this graph where you have this on your number line. However, in most cases, the mean is not 0, so we're going to have to do a z-score conversion to make it be the standard distribution. Now, when you have table A2, it's 2 pages. One page has negative z-scores, one page has positive z-scores. Each value, again, is cumulative area from the left of your z-score. When you work with a graph, make sure you know the difference between z-scores and areas. So the z-score is going to always be the mark on your axis. Okay, so let's say my z-score is negative 1.5. So that's going to be a position on the axis. Area is the region under the curve, and the areas are in the body of the table. Okay, so like if I wanted to know the area to the left, I would look up my z, and in the body of the table that would give me that answer. So if we wanted to find the area to the left of z is at the mark z equals 1.27. So notice this is less than. So the probability, that's what this p is, probability that our value is less than 1.27. So I go and I draw a picture and I approximate where 1.27 would be on the number line. I look up 1.27 in my table, and this is going to be my area, 0.8980. Okay, so this right here is also a percent. There's an 89.8% chance that my probability will be less than that value. So here's how we would look it up in the table. So it's 1.2, that's going to be my where I look in the z, and then I have to go up to the hundredths position, 7, and I put that together, and here's my particular area to the left. So the probability that a random adult, for this graph is referring to bone density. So the probability of a random adult having a bone density less than 1.27 would be 0.8980. So using that same test, let's find the probability that a randomly selected person has a result above negative 1.0. That's considered to be in the normal range of bone density readings. So always draw a picture. All right, so my z is negative 1.0. And so we're going to look up negative 1.0 in the table. Now notice though, we always want to shade the region that is under the curve that relates to the probability, okay? So this is asking us to find probability that a person has a result above negative 1.0. So above is to the right, so that's why I shaded to the right in pink. Okay, so, but we always look up the z. Now when I look it up, negative 1.00, I get 0.1587, so that's always to the left of my mark. When we want to know area to the right, the total area under the curve is always 1 or 100%, so you just have to subtract the left side area from 1 to find the leftover area to the right. So 0.8413. Always make sure that your answer is logical. So if you said my answer was 15.87, but you look at your area under the curve and you see that, well, that's a really small percentage, and this is obviously a really large, this is greater than 50% here, because 50% would be in the middle. So use some logical reasoning here to make sure that you remember to subtract the area from 1. Assume that the readings on thermometers are normally distributed with a mean of 0 degrees and a standard deviation of 1 degree Celsius. So notice that the mean is 0 and the standard deviation is 1. That doesn't really happen all the time in real life situations, but because it happened here, this is a standard normal distribution. A thermometer is randomly selected, so we're selecting one thermometer randomly. We want to find the probability that that thermometer gives us a reading less than negative 2.75. First, draw the picture of less than negative 2.75 on your normal distribution curve. So I approximated where negative 2.75 would be, and I want to find the area less than, so I shade area to the left of my mark. Okay, so I go to my z-table and I look up negative 2.75. So negative 2.7 is here. The 5 is the hundredths position, so then we put it together and I get 0.003. So the answer is 0.003 or 0.3%. Okay, so same situation, but now we want to find the probability of getting a reading greater than 1.96. So we first draw a picture of greater than 1.96. So I graph where 1.96 would be on the number line. It's to the right of 1. And because it's greater than, I want to find area to the right. So I look this up in my z-table. So I have 1.96 and my area is 0.975. Now that is area to the left. So I need to subtract that from 1 to find area to the right. So it's 2.5%. So about what percent of the area is between z equals negative 2 and z equals 2, or within 2 standard deviations of the mean? So this is giving me a between, and it's giving me 2 z's. First, draw a picture of this situation. So between, I want to graph both of my numbers and shade between them. Now, when I look this up in my z-table, negative 2 would be negative 2.0, and then you would look in your hundredths position, it would be the 0. Okay, so then that would correspond to an area of 0.0228. Now, that is area to the left of negative 2. That's not the area that I want, though. Whenever you have a z, look it up. So now I need to look up 2. So I'm looking up z equals positive 2.00. And that's going to give me area of 0.9772. So from 2 all the way to the left, that's 97.72%, or 0.9772. Now both of these areas overlap each other. They're both going to the left. So if I just want to know from here to here, I just need to subtract. So when you have 2 areas, or when it's a between, you're always going to subtract the areas that you look up. So the area between is 0.9544, or 95.44%. So we draw a bell-shaped curve and we identify the region under the curve that corresponds to the given probability. If that region is not a cumulative region from the left, work instead with a known region that is a cumulative region from the left. Using the cumulative area from the left, we're going to locate the closest probability in the body of table A2 and identify the corresponding z-score. So what we're going to do now is we're going to practice backtracking. Like if I know that my percent is 95% to the left, I can backtrack and figure out the position of the z-score that corresponds to 95% area. So here's a picture showing area to the left is 0.95, or 95%. I want to know, what is the z? Now notice the way that we set this up. I was thinking, well, if it's 95% to the left, my z has to be kind of way out here. It's definitely to the right of 0. And we have our leftover area is going to be 5% to the right. Now this is corresponding to a percentile question. Percentiles are measures of position where you're comparing your score to everybody below you. So if I'm asked to find the 95th percentile, that means 95% of the people are below my position. So that's why we graphed it like this. We have our position on the number line and we have 95% to the left. So I need to backtrack and figure out, what is that z? So let's go ahead and look at a z-table. So let's look at the z table. Okay, so what we're doing is we're scanning through, so I'm looking up the 95% area. Okay, so that's not a z, so don't look here. You're looking in the body of your table and you're trying to find the closest area to 0.9500. So you can see here that these areas are too small, so I'm going to need to go to the positive z-scores because obviously my number was positive for z. Okay, so we scan through and I can see that as I'm looking through this particular row, 0.9463, 9474, see it's getting closer, and then so right here, this doesn't happen all the time, this is a special z. So between 0.9495 and 0.9505 there's an asterisk, so if I follow that down, here, this is a special area and it has a special z-score. So the z-score that corresponds to 0.95 or 95% is 1.645. Using the same bone density test, find the bone density scores that separates the bottom 2.5% and find the score that separates the top 2.5%. Okay, so notice how I have my graph set up where I have the bottom 2.5%. So if I move the decimal 2 places to the left, that's 0.025. So I have some negative z-score that has 0.025 to the left, and I have some positive z-score that has 0.025 to the right. Now when you have a position like this where you have a right and a left, always look up the one that's on the left because that's the way your table's set up. It's always left, not right. So I'm going to look up in the body of my table and I'm going to scan for the 0.025. Okay, so look up this is giving us a different way to do it, but you can actually, I'm going to show you two ways. So let's first look up 0.025 in the body of the table. Okay, so as I'm scanning here, now remember that value that I was pointing to on my graph was, it looked like this, and I had some z way out here, and it had 0.025 to the left of it. So this is obviously on the negative side of the number line. So I'm going to look at the negative z-scores. I'm going to look in the body of the table for 0.025. Okay, so 0.025, as you scan through, you're looking here, so just scan through the numbers and try to find the closest to it. You won't always land exactly on it. So I do have exactly 0.025. So what's the z that corresponds? So you have to go over here. It starts with negative 1.9, and then to get the hundredths position you have to look up. So if I look up, I have the 6. So the z is negative 1.96 at that particular position. Okay, so that's how we got this z right here. Now because of symmetry, if I found that this is negative 1.96, then symmetry tells me that the other mark would be positive 1.96, and that's going to be the position that's going to have 2.5% to the right of it. So you can always look up the left side one, the 0.025, and then with symmetry you can just bring that number over and make it positive. Now this is showing an alternative. If you wanted to, you could figure out the cumulative area to the left of this mark. So if I know that it's 0.025 to the right, then 1 minus 0.025 gives me 0.975 to the left. So the cumulative area to the left of that is 0.975. And then I would look up in the body of the table and I would try to find the z that corresponds to that. When I do that, I'm going to get positive 1.96. So that will give me, that's how you could look up the positive value first. Because of symmetry, then you could know that this would be the negative value. If 3% of the thermometers are rejected because they have readings that are too high, and another 3% are rejected because the readings are too low, find those two readings that are the cutoff values that separate the rejected thermometers from the others. So let's draw a picture of this. So I have an upper 3% and a lower 3% that's rejected. So I'm just estimating this. I don't really know exactly the position on the number line, but I'm just estimating where it is. And I want to work backwards. Okay, so let's look in the body of the table for a number really close to 0.03. Now, this one is going to be a situation where it doesn't land exactly on the number. So let's look at the table together and see what that looks like. Okay, so I'm going to scan through the body of this table and I'm going to look for the number closest to 0.03. And again, I'm on that negative side of the curve. Okay, so I'm going to look up 0.03 and I'm looking at, it looks like it's starting over here at this row here. Okay, so then you're making a choice here because it's not exactly going to be on the table. So you're making a choice between here and here. Sometimes it's obvious, the distance, other times it's not, and you got to pick the right one because it affects your z. So which one is closer to 0.03? Well, to determine that, you could find these distances. So let's find the distance from 0.0301 to 0.03. So 0.0301 minus 0.03 gives me 1 times 10 to the negative fourth. Okay, so that means I have 1, 2, so it's this value here, so 0.0001. Let's find the distance from 0.294 to 0.03. So do 0.03 minus 0.294 to find that distance. Okay, so this gives me this. So which one's closer? The one that has the smallest value. So 0.0001 is smaller than 0.0006. So that lets me know that the 0.0301 is closest to 0.03. So the z, if you backtrack, that goes with that is negative 1.8, and here's the hundredth, 8. So negative 1.88. Okay, so now that I've determined that, I have my z, negative 1.88. Because of symmetry, then I'm going to know that the other score or the other temperature reading is going to be positive 1.88. And this is technically, if you're answering this, in degrees Celsius.